The first speaker is going to be Dr. Jeff Rowe, and most of you probably know Jeff already. He's been working with pavement since joining the industry in 1976. So just to help your math, in August, he will be starting his 50th year in the pavements industry. So yeah. President of Abatec, and the RIA software, I'm sure a lot of you know that. He's the one who taught me how to use that and stuff, so he's kind of one of my teachers in that way as well. So of course he has provided software packages for FWDs, material property analysis, rheology, leads various research efforts on materials, development specification, past president of AAPT, and US expert task force on asphalt binders till they ceased to exist in December 2018, and sits on many advising groups in North America, Europe, Asia, and Africa, and has over 100 peer-reviewed publications, many on advanced materials and performance evaluation. And his topic for today is developing a specification for asphalt binders using the DSR to determine high stiffness properties in place of the BBR. And just a note to all the speakers, I'll be sitting in the front. When you hit 20 minutes, I'll wave my hand. If you go past 26, I'll probably start screaming and stuff, so let's not do that. All right, Jeff, it's all yours.
Thanks, Deb. It's great to be back here in Laramie. We've got up early this morning, and a few of us went up and saw the sunrise on the beautiful snowy range. So, you know, I thank my friends who got up with me, and we drove out there. It's really a great two of us went up. And
the front, when you hit 20 minutes, I'll wave my hand. If you go past 26, I'll probably start screaming and stuff, so let's not do that. All right, Jeff, it's all yours.
Thanks, Deb. It's great to be back here in Laramie. We've got up early this morning, and a few of us went up and saw the sunrise on the beautiful snowy range. So, you know, I thank my friends who got up with me, and we drove out there. It's really a great place to be to talk about asphalt for a week. So anyway, what I want to talk about today is a topic which we've been looking at, about how we can use the DSR in place of the BBR in specifications. And there's a few of us who are working together on this, and there's a picture there of all my cohorts in the industry who, you know, I'll acknowledge and give thanks to for cooperating with me on this. Many of those you know, John D'Angelo Galen, Bob Gardner, Andrew Hans, Wes Cooper at the Asphalt Institute, Walter McGowan, University of Mass, and Tom Bennett at Rutgers. And the plan is to try to develop what we're talking about here as an ASTM standard and move forward with that. But basically, the objectives is to define the asphalt grade of a binder using rheology and using the DSR in place of a BBR. Part of my motivation for doing this is, you know, I go to, say, some countries which are tropical, and you say, well, we're going to do a BBR test, and we're going to test at -12, and they look at me as if I'm daft. Well, they say, well, we never get to -12, but we know we still want that good rheology. So how do we get that good rheology, but we do something a little bit different? So if I look at the perceived advantages of this method, we can have some lower testing equipment costs. We have more rapid testing. We have a lower amount of material to age. Everybody wants to get to age the minimum amount of material. We have easy training and certification. We have one less piece of equipment that we have to train and certify folks for. More acceptable in those tropical and subtropical countries if we don't have to use a BBR. And overall lower costs and less technician time. So basically what I'm trying to do is advocate that we don't need to necessarily use a BBR to test our binders. Think about why we have a BBR. BBR was developed 35 years ago plus. You know, this is during the SHARP program. Back then, I didn't have a cell phone. I mean, we all now have these advanced computers in our hands. Back then, we were working with 286 machines. I was sitting in the lab with John Reed here. We both were sitting in the University of Nottingham, and we were working with old-style computers, what we'd call old-style now. I remember, we used to have 3 megabytes of memory on a computer, and that was big. So things have changed. So we need to think about the change in instrumentation and what we need to do. The drive to change the specification and get away from the BBR has been something that the industry's been looked at. We have the icicle method that was being developed, incremental creep loading. But that has a customized and proprietary database. You have to have an online link for that. John will tell you that if you're working with Shell or other oil companies, they probably really don't want you to have an online link, a live link to go and analyze your binder data. So maybe that's not the best solution. 4mm rheology, has been developed here. Other people have been looking at it, but there's a bias in that. I've done results and studies with 4mm. I see a bias. There's no standardized procedure yet. Texas has its method. It's introduced recently for looking at doing tests in a DSR at low temperatures, but you need to have a chiller with that machine and more advanced rheometer. I should just mention before we go on, there was a QR code on the very first slide. I have the same QR code on the very last slide, so you can download it. I'll leave that last slide up. Very last slide, you can download this presentation, so you don't have to take pictures. Just make sure you grab that QR code at the end. So what my objective here is to talk about, what methods we can look at for trying to classify the low temperature properties, or I really should say the high stiffness properties of binder with a more robust method. So that's really the objectives we're looking at. So think about what we're trying to do. The stiffness in a bending beam rheometer, 300 megapascals. We have an M value of 0.3. They've been related to low temperature cracking. And then we have this other parameter, delta TC, which is considered as a durability parameter. Delta TC defines the shape of the master curve, and we know that we have other parameters that can give us better definition of shape, things like the R value. Pavel Chris introduced the phase angle at a constant modulus. We can look at the crossover modulus. My favorite out of those is the phase angle at a constant modulus. S&M define point parameters measured at 60 seconds. And we use 10 degrees above the PG low temperature grade. That was something that was introduced during SHARP. It doesn't quite hold true, but I'll show you that in a minute. We can use the principles of time temperature superposition to get alternate parameters for the S&M and the delta TC. And that's what I'm going to show you in the work that we're doing here. So we published this in 2014 at CTAA, and this shows the interconversion between the G star and the S of T and the phase angle of and M. So let's see if this works here. So we have, here you have S of T. This is the conversion to G star. So if you have a stiffness of 100, you can come across and you've got your corresponding G star there. The G star of 100 is where your 300 megapascals is. On the M value, it's a little bit more scattered, but the M value, this is the M value. If you're here 0.3, that comes across to about 27 degrees. So that's the interconversions that you have. They're fairly robust. If you look at other interconversions that have been published in the industry, the work done in France back in 91, or actually 99, but it goes right back to the early 90s. They looked at a temperature where the phase angle is 27 degrees, and they said that's related to cold temperature cracking. If you look at work being done in Canada, in Ontario, they're looking at 30 degrees. So what we're doing here isn't in isolation. Other folks are also looking at this temperature with a phase angle. And these are consistent with the analysis done here in the NCHRP 960 work. They've done some interconversion work as well. And what we're saying is, well, you could round those numbers. You could use G star of 100, phase angle of 27. They correspond approximately to the stiffness in the bending beam of 300 and the M value of 0.3. And if you have to remember that, you know, E equals 3G approximately. So that's your interconversion. So what we've done, the methodology that we've basically followed is we've run these full master curves. We've looked at BBR and DSR master curves. We've combined these in our software, and we've calculated using this analysis what the temperature that would correspond to the M value of 0.3 and the temperature where the stiffness is 300 megapascals. So we're basically determining the temperature of those numbers, and then we're determining the temperature of the equivalent interconverted numbers at 10 radians a second. We've been very careful in our work to make sure that we work in the linear viscoelastic region. So if you test materials at higher strain levels, so for example, if you look at ASTM D7175, it talks about strain levels of 1% and 10% and 12%. Well, you have to drop those strain levels because you're measuring at higher stiffnesses. So, you know, we're working down at 0.5% strain, lower strain levels, just to make sure we're in the linear viscoelastic region. And that's sort of quite an important consideration. And then the other thing that we've done is we have the method where we've worked with the master curves, and we've also developed this simplified procedure. So this simplified procedure, basically we're taking a test at a certain temperature, and we're using 10 radians a second. We're measuring the G star and the phase angle, and we then drop the temperature. We go through an isothermal drop in temperature, measure G star and phase angle again. So this is a bit like your normal testing for the intermediate temperature, you know, where you test it for the intermediate temperature. And we've done this for a bunch of binders where we've dropped the temperature and we've got the G star and the phase angle, and then we can compute a whole load of parameters. So we've used this for both the intermediate parameters and looking also at the low temperature parameters. If you did this for the whole set here, this takes, what I show here is about a 2-hour testing window, but if you only want to do the low temperature part and the high stiffness part, then that drops down to maybe half an hour, something like that, in terms of a test procedure. But it really depends how far you want to go in terms of getting the data out. So this is a simplified procedure. This procedure has been submitted to ASTM and is in the ASTM draft procedure. It's been through a ballot, and Wes Cooper is looking at this with the Asphalt Institute. So how do the results compare? These are some graphs now that show the data sets in terms of the temperatures. I can't quite see when I turn around. I have to look at this screen. And I'm going to turn that a little bit so I can see that. So on this side, we have the temperature of the M value from the bending beam rheometer, and the temperature that corresponds to the phase angle of 27 degrees. And you can see that there's a very good correlation between those plots. And what we did is we looked at some different parameters. We looked at the temperature where the phase angle is 30 degrees, because that's what they're doing in Canada. The 27 degrees gives you a better correlation, so we prefer that one. And then we looked at the G star interconversions, and we get a very similar interconversion whether we use 111 or whether we use 100. It's very, you know, you're talking about the third decimal point in the R squared in terms of how those data points compare. So we've sort of gone along with using 111 and 27 as our numbers to adopt from this interconversion. Delta TC correlation is not quite so good. Delta TC is a little bit problematic in the industry as a whole. The work being done by the Asphalt Institute is probably going to suggest that we don't move forward with the delta TC and we use Pavel Chris's approach instead. But it's still, the correlation isn't too bad, but when you're measuring delta TC, you're measuring a slope of a very flat part of the curve. So when you're measuring the slope and it's a flat part of the curve, any small error is magnified in that delta TC. So, the comment here is that industry recognizes that delta TC is a poor shape parameter and is most likely to be replaced with the modulus, the phase angle at a constant modulus. I've slipped forward. I wanted to show you this one. We use we're going to use time temperature superposition in terms of trying to fix test temperatures. One of the things that's poorly documented is the temperature shift of this 10 degrees C that we have in the bending beam rheometer. And this shows you that it basically doesn't quite work. The 10 degree shift is a little bit off. It really is giving you something which is not quite 300 megapascals, but is closer to, say, 150 megapascals when you do the shift. This was also documented in a TRB paper around about 2013, 2014. So this is not the only work on that, but it doesn't quite work in terms of the shift. If we do a similar analysis to the 10 degree shift that they did for the bending beam rheometer, to go from 7,200 seconds to 10 radians per second, our shift is 28 degrees. And we've done this in a fairly robust way. The initial 10 degree shift was in a less robust way. If you do 10 hertz, that shift becomes 34 degrees. So some of the folks in Europe prefer to test at 10 hertz. I don't really have a strong feeling whether you test at 10 hertz or 10 rads. It's really a question of what that shift is going to be. And that shift is relatively consistent. We looked at some binders from Arizona. This was looking at 5 binders. They are different levels of modification, some conventional binders, just to see how that shift varies going from 10 rads to 10 hertz. And there's a 6 degree shift there. And if you look at the variation that you get, this was going from 15 degrees C to 9 degrees C. And you can see there's a little scatter there, but you're all within a degree in terms of that scatter. So it's not too bad. I think it's reasonable enough, especially when we consider what we were founding this on was the original shift of 10 degrees C. We're probably more accurate than that original shift in terms of what we're doing here. So in terms of looking at the two methods, looking at the analysis from the full frequency sweep method versus the simplified method, we've only got a limited number of data points here. I can't really put an R squared through the green data points. I could put a root mean square error there, but doing an R squared would make no sense at all. But these are some binders that come from New England and part of a study we're doing in New England, and they're reasonably close in terms of the grade evaluations, looking at the simplified method versus a full master curve method. So the analysis or the result from this work says you don't need to do full master curve. You don't need to have my fancy software to do this. You can do it with a much simplified method, running a standard script in a DSR to get the numbers. And this is very important because folks want a simplified method that they can run in the lab. Other options that exist, this is some work that was done for Wisconsin DOT. Tom Bennett and myself developed this as a procedure where you can relate the Glover-Rowe parameter at 15 degrees C and 10 rads to the M value. So that was for the Wisconsin DOT binders. And there was a set of binders there. They're largely M-controlled binders, so that correlation might not hold true for everything. It was on a limited set of binders. And then also we can take an R value calculation as well from that method. So we can have both a point and a shape parameter from a 10-minute test in the DSR. And if you think about that, that's a very rapid test as a screening tool to get your information from a DSR. So there's two procedures there. One is like a 10 to 15-minute procedure. The other one is a half an hour to maybe an hour procedure by doing the temperature steps. So two alternate procedures. And then you can say, well, this would be your grade equivalence. So Olga Pudzik originally had this concept of trying to look at boxes for where your grades might be, and this would be a 6422 grade. Well, if you did the test at 10 radians per second in a DSR, you'd be doing the test at 64 and 6 degrees C. Okay, so that's quite a big difference. If you think about the ease to do a test at 60 degrees C versus trying to do something at -12, it's a lot easier test to run in the lab. So that's the goal here, and it's a lot easier for me to go and implement that if I'm working in Tanzania or somewhere else in the developed world. And I can tell you some horror stories about trying to implement BBRs in some of those countries. So this is my goal, is to try to make this as an easier procedure for trying to implement performance grade binders in some locations. In summary, what we have is a procedure where we can enable low temperature PG grade estimation without the need for BBR testing. I'd say that we have excellent correlations between the methods, between the BBR and the DSR. We can use either 10 rads or 10 hertz. There's a 6-degree difference between the use of those two temperatures. That enables us to significantly increase the test temperature, thus avoiding the need for complex chilling units and doing tests at cold temperatures. And we can use this to rank binder performance. Testing scheme at using a 0.1% strain level and 6-degree temperature steps is going through the ASTM procedure at the moment, and Wes Cooper has been sort of putting that through the procedure. The other thing I should mention is we're using a similar procedure in the roofing space as well. So, this type of analysis has also been looked at for roofing grade binders as well as paving grade binders. And, we may also, this may impact the amount of binder that we need to age, so we can also have the opportunity to look at some alternate aging procedures. And with that, I'm going to stop. That's my QR code, so if you get that, you get the whole presentation without having to take pictures. Deb, thank you.
Yeah, questions for Jeff, please, and please on the mic, first introduce yourself and then ask. Thank you.
Raj Dongre. Jeff, I know you for most of your asphalt career, and it's a good effort that you're doing, Jeff, especially for the other countries, the tropical countries, and I can understand your problem there. But you left out a couple of things of why we were doing the BBR. One of the major things was that we wanted to test under tension and not under shear. And I don't know if you remember, but there was a person that showed that you could just use the DSR and essentially use sawdust as an additive to affect the shear properties, but they wouldn't function in tension. That's number one, right? And getting this E to G of 3 is an approximation. The second thing is the reason the BBR was developed with the air bearing was because the suppliers, see the way the sharp spec is that we don't cover the spread. The suppliers have to cover the spread. So the reason the BBR was developed with an air bearing is to give you precise measurements so that the suppliers don't have to bear the brunt of that spread. So it seems to me that with this kind of approximation, the suppliers will have a bigger problem trying to cover that spread in trying to estimate these things instead of actually measuring. That's number two. Number three is if you think that saves you money and time, as an asphalt laboratory owner, I'll tell you, DSR, you can barely get 8 tests done in a day if you're lucky if you tie the technician to the DSR. So it really, what you're saying really is that go buy another DSR and hire another technician and maybe you'll save some time. And number 4, I would proffer that I can go from BBR to the high temperature just as easily without even aging the material. So I don't know that this effort, which is a good effort for tropical areas and everything, but for US where you have low temperatures and you're interested in tensile stress condition to test, I would not recommend something like this. Now you can tell me why I'm wrong.
Well, Raj, look at those correlations between the flexure and the shear. I mean, I hear what you say, but the correlations hold true.
Right.
And if what you're saying is why have the 4 millimeter? Why have the icicle? Why have the Texas method?
Right.
The industry wants a method that they can do something with the DSR as doing it, without necessarily doing a proprietary system or something which is non-standardized. What we're trying to do is put a standardized procedure there.
And I hear you, okay? And you can, if you phrase this as a screening tool rather than a specification tool, I would agree with you, because we can now even go further. The ABQT with the PG grading system, you don't even need to do RTFO or PAV aging, and in 5 minutes you're getting your whole continuous grade. So what this is pointing to is that asphalt itself works, meaning the PG grading system that we have put together works, even if you test original asphalt without doing RTFO. That's the message that is coming out of this thing. So we don't really need it. We force people to do RTFO and PAV thinking that that's going to really solve the problem. But it seems to me that the same grading exists in the original condition of asphalt also. So why not go all the way and use this ABQT to get your grade in 5 minutes? And the correlations there are fantastic, even better than this thing. So, for tropical places, I would agree, but for saving time and for, if you do it as a screening tool, fine. But as a specification, I think we are missing the point of doing the whole tension stuff and having precise measurements. Those points will miss out if we go this path. But of course, you have a lot of important people in that picture there, and if they wanted, they would probably push that through. But this is a whole consensus thing. But I would just caution that if you're a supplier and if you're trying to cover the spread, when you start predicting stuff, it becomes a little bit different.
Yeah. I mean, the other comment you made, Raj, I have to address is I don't believe you can get high temperature properties from a BBR because your deflections are way too big to get high temperature properties.
Jeff, I'll show you next year. I've already done it. That's AI. That's what AI gives you, the ability to leverage old data and produce these things, and I'll demonstrate it to you next year. It's a promise.
We look forward to that, Raj.
I think we got a question from the chat room.
This is from Gail Keene. Does this approach work for PMA? What about low temperature fracture properties? Tale of two deltas?
Well, we have evaluated in the Massachusetts study that I showed you. There was a series of PMAs, crumb rubber modified binders and conventional binders, both the base binders and the modified version of those base binders. So, I think it holds for pretty much everything we've looked at. So I'll answer that for Gail.
All right, my name is Terry Chen. I work at Canon Instruments. So I'm very interested, very interested with the presentation that you give. So actually in June, I was talking with Wes Cooper at the ASTM conference, talking about developing a new ASTM standard. So my question to both Wes and you is like, this is a great test. The DSR, actually dynamic temperature ramp experiment or dynamic TTS type of measurement, is a great accurate measurement for the current temperature window. So my question to you is, I'm actually kind of agree with the other gentleman's concern, is like whether or not this test is really representative enough to really being able to use to predict low temperature performance. TTS is a great tool for not very heavily filled asphalt system, and also not going through a bigger temperature range. I see from your presentation that some of the data at lower temperatures start to deviate more. So then the question is, are you really able to use this technology to predict the performance at lower temperature instead of directly doing the measurement at low temperature? And the other thing is like, the reason BBR is still existing is because, you know, there is a complicated procedure. People don't like it. There are cons in that procedure because you use liquid and it's really time consuming, but there is a reason for those kind of conditioning because you do need to age the sample for that kind of long time. And also TTS, under those kind of lower temperature condition, you may have to consider some B shift, a vertical shift, instead of purely just horizontal shift. Do you agree with that?
Some of what you agree, some of what you say, I mean, I'll make a couple of comments. I mean, first of all, the BBR is a good rheometer. It gives you very precise information. I don't have a problem with the BBR as a tester instrument. But if we are trying to develop alternates, I think a DSR gives you absolutely good results. BBR is a test in flexure where you're basically, the beam is half in compression, half in tension. That's not what causes thermal cracking. Thermal cracking is a pure tension. So you don't have the same condition in a BBR test as you have in a thermal fracture in a road. That's why they developed the direct tension test for mixture work. So, you know, we can talk about the difference in stress states and the difference in conditions, but whichever way it is, both tests are not giving you the same condition. So both tests are extremely well correlated. Sure, at the extremes, because the materials are getting different, you might get some different results. But, you know, this is a work in progress. And, you know, the Petersen Conference is always about presenting work in progress. I mean, that's what we're trying to do here, present ideas. We have 3 methods in the industry at the moment which are being presented and advocated as alternates for BBR. I'm presenting something that makes use of an existing standard, ASTM D7175, with a very minor modification. So there's nothing proprietary in what we're doing here. And I think it's a perfectly acceptable way of getting good information about your high stiffness properties that we have. So, you know, I understand Canon wants to sell BBRs and, you know, I understand manufacturers want to have the devices in the marketplace. And I love Canon machines, you know, they're great machines. But I think we have some alternates.
So can I come?
Sorry, I have to, it's already 30 minutes. And Jeff will be bored during lunch if you don't talk to him. So find him wherever he is eating and everybody just go. I'm sure he will enjoy that. Let's give a round of applause to Jeff.
Thank you.